Hello everyone, my name is Oumayma Chdil, PhD student supervised by Professor Balli Mohamed. Today, during this presentation, I will discuss with you the influence of copper oxide secondary phase on Pr1-xSrxMnO3 Magnetocaloric features. Magnetic refrigeration is new refrigeration technology that is more respectful of the environment and less energy consuming. It's based on the Magnetocaloric effects, which is an intrinsic property of certain magnetic materials. The used material in this technology must have a giant magnetocaloric effect. So there are a very large number of magnetocaloric materials which have been studied, such as gadolinium and other intermetallic materials. But those materials oxidize easily, resulting in the degradation of the thermodynamic performances. For this reason, research activities have been directed in recent years toward the manganese oxide, due mainly to their strong chemical stability. As a result, our experimental work is focused especially on the Pr1-xSrxMnO3 manganese type that represents a Curie transition near to the ambient temperature. The polycrystalline samples were prepared using the solid-state reaction method. Then a quantity of the calcined powder was employed in the composite preparation, where an amount of copper oxide was added and mixed well, and then the mixture was calcined at 1200 degrees Celsius for 2 hours. The first figures show the X-ray diffraction patterns of the piston and the composite one. The first sample crystallized in the orthorhombic structure at room temperature with the PN-MA space group, while in the second sample we can observe the coexistence of the two phases. The refinement results for all samples are summarized in this table. The presence of the secondary phase leads to a clear structural deformation in the main phase, where the Mn-OII-Mn band angles are clearly modified. In the following figures, we present same micrographs of the two samples and also the EDX spectra, which indicate the presence of different chemical elements. The copper additive effect is really apparent in the composite material micrographs, where the main grain size is increased from 0.5 micrometers to 4 micrometers. On the other hand, here we have the magnetic measurement. So from the lowest value of the dMdT as function of temperature, we can estimate the Curie transition. So by adding the copper oxide, we can observe that the Curie temperature decreased remarkably from 293 Kelvin to 274 Kelvin. And here, based on the measured magnetization curves, we can observe that below the Curie temperature, the magnetization curves exhibit non-linear patterns with a tendency to saturate in the presence of magnetic fields, indicating then a ferromagnetic property. However, above the Curie temperature, the magnetization evolves almost linearly, indicating a paramagnetic state caused by the thermal agitation of the magnetic moments. Moreover, and based on this obtained result, is a thermal magnetic entropy change caused by the variation of the X-ray magnetic field can be determined using the well-known Maxwell relations. The change in magnetic entropy as function of temperature of the two samples are shown in the following figure. As observed, the highest magnetic entropy change for the composite one approach to 1.8, well, it's approximately 1.2 for the Pr1-xSrxMnO3 under 1 Tesla. A variety of mechanisms may explain this reduction in transition temperature and magnetic entropy. To start, there is a loss of ferromagnetic interaction caused by the inclusion of the copper oxide. Second, the presence of copper oxide altered the double exchange interaction through the remarkable structural deformation. The high grain size of the composite, on the other hand, may promote more ordered ferromagnetic phase and therefore reduce the width of the magnetic transition. Finally, I would like to thank my supervisor, our collaborators, and you for your attention.